38 months. That is how long China took to build the world's largest train station, on a mountain. Most countries take longer than 38 months to approve a planning application. 2 million cubic meters of concrete, 366,000 tons of steel, 40,000 workers, 1.2 million square meters of floor space, a roof weighing 16,500 tons, and a clock that never stopped. This is Chongqing East, the world's largest train station, built in 38 months. The mountain was not an empty space. It was a wall, solid, inhabited, and unforgiving. On May 16, 2022, the first controlled blast shattered the calm, sending ripples through the eastern slope of Nan'an. Sensors buried in the ground tracked every tremor. Peak vibration never exceeded 0.2 G, in strict compliance with national safety codes. The city above barely stirred, but below, the earth shifted by meters at a time. Excavators rolled in behind the shockwaves. Each machine clawed out rock and clay, loading it into convoys that never stopped. 3 shifts of 10 hours each, 40,000 workers rotated day and night. In the first 4 weeks, more than 400,000 cubic meters of rock disappeared, enough to fill 100 Olympic pools. By July, the mountain's original face was gone. In its place, a stepped bench cut with geometric precision. Satellite images from September show a 200-meter-wide scar, the first-level ground carved from a 30-meter drop. The logistics bordered on military. Detonation crews, dust suppression teams, water trucks, and debris haulers all moved in sequence. Temporary roads snaked up the slope, rebuilt every few days as the excavation advanced. Each blast was calculated to avoid damage to nearby homes, many just a few hundred meters away. Complaints about the noise and dust reached City Hall, triggering a wave of mitigation plans, acoustic barriers, daily misting, and strict limits on night work. Workers like Zhang Wei, a rebar tier with 12 years on mega projects, watched the first night blast from the edge of the exclusion zone. He later described the ground shaking beneath his boots, the air thick with grit, and the sense that something irreversible had begun. By August, the mountain was no longer a barrier, but a vast, level platform, ready for the next phase. The original landscape, millions of years in the making, was erased in a matter of months. Passengers arriving here now step onto polished concourses, never guessing what it cost to make the ground flat. Nothing about the new plateau was stable, not yet. The raw bench left by the excavators was just a temporary scar, unsupported and vulnerable to the mountain's pressure. Engineers moved fast to lock it down. First came the permanent retaining walls, reinforced concrete 30 meters high, stretching along the cut face. Each wall was more than a barrier. It was a counterforce holding back thousands of tons of rock and soil that wanted to reclaim the flat ground. The geometry mattered. Every curve and corner was calculated to resist sliding and overturning, with the wall base anchored deep in undisturbed strata. Water was the silent threat. Groundwater trapped in fractured rock could build up behind the walls and trigger a landslide. Crews drilled a network of dewatering wells, dropping the water table by 3.5 meters. Horizontal collector pipes 200 millimeters in diameter threaded behind the walls, channeling seepage into sumps. Sensors logged groundwater pressure every hour. By September, piezometer readings showed steady decline, proof that the subsurface was drying out, the risk of uplift and erosion falling with each passing day. Only then did the pile grid begin. Each foundation pile, driven to a depth of 35 meters, had to pass a static load test. Settlement under maximum design load was less than 5 millimeters, well within the margin for a structure of this size. Lu Fen, a junior technician, spent her days calibrating the gauges that tracked every shift in the concrete and steel below. Her logbook records the numbers: wall deflection under load, groundwater drop, pile movement. No surprises, no sudden spikes. That was the goal. The invisible work of walls, drains, and piles would soon vanish beneath 8 stories of concrete and steel. But without this hidden choreography, the mountain would have taken it all back. Now, the platform could bear the weight of a city. The risk had been engineered away, locked behind concrete and data, 1 millimeter at a time. Columns rose before the roof ever moved. Each one, 41 meters tall, was shaped like a tree. Steel shells hand-fitted with 1,200 stainless steel scales for light and strength. They arrived in 4-meter segments, bolted and checked for plumb, then locked to the mountain's new core. The columns were the only things ready to bear the full weight of what came next. A single steel canopy, 16,500 tons, covering 120,000 square meters. The roof was too big for cranes. No machine existed that could lift it in one piece, not in this terrain. Attempts to model a gantry system failed outright. There was nowhere for the towers to stand, no way to keep them stable on the cut slope. Every calculation pointed to disaster. The ground would shift, the load would twist, the risk of collapse was real. Engineers turned to hydraulics. 74 jacks, each rated for over 220 tons, were arranged in a grid beneath the assembled roof. The control system was a network of sensors and PID controllers, each jack communicating with its neighbors 100 times per second. The margin for error was plus or minus 1 millimeter. Any more and the roof would warp, binding against its own weight. On January 6, 2023, the system was commissioned. Test lifts began with a 4,400-ton mock section. Every morning, technicians recalibrated the jacks. Pressure logs showed a nominal range of 0.98 to 1.02 megapascals. Even a 0.5 millimeter drift triggered an alarm. The actual lift happened in May. The entire canopy, 5.5 hectares of steel, rose 23.7 meters in a single continuous motion. It took 9 hours. The roof did not tilt, did not buckle. Sensors logged a maximum deviation of 0.2% across all jacks. Once at height, the structure slid horizontally onto its permanent bearings, guided by rails machined to fractions of a millimeter. The world's largest roof lift was completed without a single injury or uncontrolled movement. Liu Fen, a technician on the jack crew, described the moment in her logbook. Every millimeter mattered. A 0.5 millimeter drift could have twisted the roof. When the pressure spiked, the safety valve saved the crew. There was no room for mistakes. Now, the tree columns hold a roof that no crane could lift, and the mountain summit is gone, replaced by a canopy that floats above trains and passengers, its engineering all but invisible to those who pass beneath. The roof settled into place, but precision work continued on every surface. Curtain wall panels, each 2 meters square, arrived pre-assembled, glass and aluminum engineered to fit within a 5 millimeter margin. Robotic gantries guided them into position along the east elevation, sensors monitoring every shift. The final data showed a maximum deviation of 3.7 millimeters across the entire facade, well within tolerance. By midsummer, the building's skin formed a seamless, reflective shell. Beneath the platforms, the metro tunnel demanded its own vigilance. Its crown sat just meters below the main slab, vulnerable to the slightest movement above. Settlement sensors embedded in the tunnel's lining tracked every micron as 16,500 tons of roof steel rose overhead. The result was less than 2 millimeters of shift. No leaks, no cracks, no need for repairs. The tunnel's waterproofing held, its bore untouched. Above, the rails required equal attention. 29 tracks, each engineered for 350 kilometers per hour, stretched in parallel across the new slab. Rail-laying trains set continuous welded rails to within 2 millimeters over a kilometer. Lasers checked alignment, while ballastless beds prevented vibration drift. Overhead, the catenary system, 25 kilovolts alternating current, was tensioned and measured for thermal expansion, each contact wire holding its height through heat and cold. Signaling formed the final layer of integration. The CTCS-3 system, China's most advanced train control protocol, underwent exhaustive testing in September. Every switch, every signal, every interlock was simulated, then run at speed. The margin for error was measured in milliseconds. In the first trial, a test train reached 350 kilometers per hour, the system tracking its position to within a meter. No conflicts, no faults, no delays. By the end of integration, the hub was calibrated to a level of invisible precision for travelers. Glass, rails, tunnels, and signals, each tuned so that the mountain, once an obstacle, now functioned as a seamless passage. Every day, passengers cross 1.22 million square meters and never see the 2 million cubic meters of mountain moved beneath their feet. Precision wins over terrain. Scale hides struggle. Infrastructure erases memory. The mountain is gone, replaced by routine. In engineering, the hardest victories vanish, leaving only possibility behind.